So I would like to welcome everyone to this fifth webinar in the discussion series on tipping elements, irreversibility, and abrupt changes in the Earth system. So my name is Didier Swingedouw from CNRS. So I'm working at University of Bordeaux in France. I'm here to convene this this webinar with Helene Hewitt. So my expertise is on the ocean and climate dynamics, and I notably had the chance to be a lead author of IPCC special report on the ocean and cryosphere in a changing climate, namely in chapter 6, dealing with extremes, abrupt changes, and managing risks. So the goal of this discussion series is to advance the knowledge on tipping elements and to support efforts to increase consistency in treatment of tipping elements in the scientific community. So for this, we developed a research agenda and designed joint experiments and ideas for tipping elements model intercomparison project, EHSMIP. So the first webinar in this series, starting in September last year, provided an overview of tipping elements and climate extremes. And since then, we have also covered the Amazon rainforest, permafrost, and ice sheets. And after today, we will continue in March with a discussion on the monsoons. So you can register for the coming events using the link in the chat box, and find back also recordings of past events, which are available on the WCRP YouTube channel. So the focus for today is on ocean and the Atlantic Meridional Overturning Circulation, AMOC, in the following. So for this purpose, we will hear a presentation that will address the potential tipping points in ocean and which role the AMOC changes could play. So before going into the introduction of the speakers, I will briefly give a short overview of the three organizations that have initiated this discussion series. So first one is the Earth Commission, which is a global team of scientists with the mission to define a safe and just corridor for people and the planet. So this will inform setting targets for a stable and safe planet, and will help us in developing and understanding pathways that are compatible with these targets. The other organization is named AMS for the Analysis, Integration, and Modeling of the Earth System Project, which is a global research network composed of Earth system scientists and scholars that seeks to develop interdisciplinary ways to understand the complexity of the natural world and its interaction with human activities. So both AMS and the Earth Commission are hosted by Future Earth, so a global network for scientists, researchers, and also innovators collaborating for a more sustainable planet. So vision from Future Earth is of a sustainable and equitable world for all, where societal decisions are informed by openly accessible and shared knowledge. So Future Earth's mission is to advance research in support of transformations to global sustainability that provide good and fair lives for all within a stable and resilient Earth system. So finally, the last organization that initiate this series is the Safe Landing Climate Lighthouse activity of the WCRP, the World Climate Research Program, which explore routes to safe landing spaces for human and natural system. So it will explore future pathways to avoid dangerous climate change, while at the same time contributing to the United Nations Sustainable Development Goals, SDGs. And now I will pass on to our other co-chair today, namely Helene Hewitt. The floor is yours.
Hi. Thanks, Didier. Really warm welcome to everybody from my side. It's really great to see so many of you here. I'm Helene Hewitt from the Met Office Hadley Centre in the UK, where I lead the Ocean Modelling Group. I was one of the coordinating lead authors for the chapter on ocean, cryosphere and sea level change in the IPCC 6th assessment report. So before I introduce our first speaker, I'll just provide an overview of today's events and the modes for interaction. So both of our speakers will present before we move to the Q&A session. However, during their talks, feel free to pose questions and indicate to whom your question is directed using the Q&A feature at the bottom of the Zoom window, and everyone can upvote their preferred questions. We will then get to these questions in a discussion session following the presentations. We've got a number of experts in the audience, and so we really want to encourage a lot of interaction. We've set up an interactive Miro board, which is a virtual whiteboard that can be used to leave comments or respond to prompts that we have provided on the board. And these can be accessed through the link in the chat box. The Miro board will be kept open throughout the week for any ongoing discussion. And following the event today, we will post the recording on the Tipping Point series Confetti webpage, so it will be accessible in the future. So moving on to the talks, it's my really great pleasure to introduce our first speaker, Professor Christoph Heinze from the Geophysical Institute and Biogeochemical Center for Climate Research at the University of Bergen. Christoph's interests lie in modelling of marine biogeochemical cycles, quantifications of the global carbon cycle, simulation and interpretation of the climatic sediment record, feedbacks between biogeochemistry, and climate and ocean tipping points. He served as a lead author for IPCC Working Group 1 in the 4th assessment report and as a review editor for the 5th assessment report. Christoph has been a member of the Norwegian Academy of Science and Letters since 2019. So thank you so much, Christoph, for being here, and the floor is yours.
Thank you very much, Helen. I will then share my screen and let's see whether this works. I will minimize the window and go full screen. And I find the laser pointer. Yes, so then I will start. First of all, I would like to thank the organizers very much for this invitation, and also would like to take the opportunity to thank the funding agencies for our research. And we'll just immediately go into a little bit of the glossary up front. So tipping point, this is from the glossary of the IPCC special report on ocean and cryosphere. And it states, a tipping point is a level of change in system properties beyond which a system reorganizes, often in a nonlinear manner, and does not return to the initial state, even if the drivers of the change are abated. For the climate system, the term refers to a critical threshold at which global or regional climate changes from one stable state to another stable state. Tipping points are also used when referring to impact. The term can imply that an impact tipping point is about to be reached in a natural or human system. And also another term in this context is often mentioned, that is the term regime shift. And I use here the wording from the paper by Biggs et al. In 2018. Changes in ecosystems and social ecological systems are often experienced as relatively slow and incremental, but sometimes dramatically large, persistent, and often unexpected changes take place. So this would be regime shifts. In this paper by Biggs, also things like the AMOC changes, sea ice changes, and so forth are mentioned also in the big table under regime shifts. So it's a very worthwhile paper to look at. And I then would like to show a little bit the different tipping types. That's from a paper, a recent paper by Vanzelov et al. And you can see here these kind of cup ball analogy, which goes back to ecosystem science. Martin Scheffer was one of the pioneers here. And this cup shows more or less the system properties, and this little ball shows the state of the system. We can have different types of tipping. So we can have a bifurcation by changing gradually for example, the system properties, and then this ball would roll from one minimum of this potential to another one. We can have the so-called end tipping, that would be noise-induced tipping, where just by stochastic movements, the state of the system could change. And another possibility is a shock-induced tipping, where shock acts and pushes the system over this hill into a new one. In recent years, there has also been paid a lot of attention to rate-induced tipping, which is illustrated here also on the left-hand side. And this is a little bit more abstract at times to understand. And I found a very good image for it in the PhD study by Claire Kears. And she compares it with, you have a table with dishes on, or first the tablecloth, and on the tablecloth you have the dishes. Then you can draw at the tablecloth, and you can have two distinct outcomes. The dishes come with the tablecloth, or they get left behind. And the deciding factor between these outcomes is not how far the tablecloth moves, but how fast. So that is a good interpretation or a picture of this rate-induced tipping. In practice, I have to say, so far, it's much easier to find cases for regime shifts, so the eventuation of a tipping, than the threshold or the actual tipping point. And to quantify this is a big challenge, and it's part of the overall efforts in many projects going on in the moment. If we go to the ocean circulation and ocean, I would like to show briefly this figure of the great ocean conveyor. So it's a conceptual model of the ocean circulation, just to show you the primary pattern with the sinking areas in the high latitudes, and then this large return flow. And the time scale is important. It's about 1,300 years for the oldest water in the ocean. So the ocean has also on long time scales. A lot of concern has been issued for concerning the collapse of the meridional overturning circulation in the Atlantic. And in order to collide here with Stefan's talk later on, I show a quite old picture, but one of my favorites is from AR4, from a series of Earth system models that simulated the change in AMOC for a strong warming scenario. And you can see that there are big differences on how far they go down, and with warming. There seems to be an agreement that the ocean circulation slows down, but there are big differences, mostly or to a big deal caused by variations in the freshwater fluxes. We will hear more in the second talk on this. I will briefly touch on another physical oceanography issue that has received attention, and this is an abrupt cooling of the subpolar gyre in the Atlantic. And this abrupt cooling has been observed in sediment cores from the Paleoclimate record, and this here is from a recent paper by Didier, showing this abrupt cooling for projections into the future. These are these blue lines here for different Earth system models, but these are tied to this subpolar gyre here, and obviously connected to changes in the mixed layer depth and the respective also heat exchange between ocean and atmosphere. And this is an important thing, because it had these are surface air temperatures, I have to say, but this subpolar gyre cooling due to processes in the ocean is an important, probably bistable mode, steered to a large degree also by salinity fluctuations. The funny thing is that this can be reproduced by Earth system model, this abrupt cooling here, but it does not appear so much in stronger forcing scenarios that may be more realistic for what we expect in the next decades. I switch over to the Arctic and Antarctic sea ice, and you see here is a nice sketch from the paper by Goos et al. there are primarily three issues discussed with respect of abrupt changes in ice cover. First is the Arctic summer sea ice loss, coupled to the well-known ice albedo feedback. But there may be also some stabilizing negative feedbacks happening, as for example discussed in the paper by Notz et al. Because if you remove the sea ice, then you have a heat flux or heat loss from the ocean, and the water cools. So it's a bit an open question. Then also one has seen, at least in Earth system model runs, an abrupt sea ice increase in the Southern Ocean within the next decades. And this is due to the fact that the warming reduces ocean deep convection, especially one has seen this in the Indian sector, and one could then form a fresh layer, surface layer, and hence also more sea ice there. Then I think the more robust concern is the Arctic winter sea ice loss, simply due to a fact that the ocean water will get warmer, and there, if it's not possible to produce sea ice at the first place, then this is probably the most critical one. And as a question also how reversible this sea ice loss is, and Helen has worked on this, and maybe she can comment also later on a little bit on this. Finally, in the polar regions concerning ice, there's also the concern about the destabilization of offshore permafrost and gas hydrates. And there are huge amounts of methane potentially accumulated in the eastern Siberian Arctic shelf seabed, and the potential for abrupt methane release exists. And we see also at present more or less continuous leakage of methane, but it's not really clear how important this can be. In any case, these hydrates are tied to a certain stability point with respect to temperature and pressure, and when this is passed, there could be destabilization. It's an open question. Going back a little bit to the sea ice, Sybren Dreifout and colleagues have investigated in the CMIP 5 models abrupt changes, and they found all different types of fluctuations, bimodal fluctuations, also regional ones, and this abrupt Southern Ocean sea ice increase could be seen in at least one model here. But the more robust thing seems to be the loss in Arctic winter sea ice. So this collapse shown in different models, and it's probably the most concern here, with also implications for the societies around the Arctic and the biology and biogeochemistry in the Arctic Ocean. I will then go a little bit to the environmental thresholds and what we can see here. I refer to the triple threat: warming, ocean acidification, and deoxygenation. For warming, it's so that there exists for many organisms an asymmetric thermal performance curve, so they are more susceptible to warming, and they can tolerate cooling better. Another concern is the ocean acidification. So the calcium carbonate saturation levels will be reached. Normally the ocean is oversaturated, but with more and more CO2 entering the ocean from the atmosphere and is dissociated into carbonic acid and other components in the ocean, like bicarbonate and carbonate. We see a pH change, and then mostly these organisms with calcareous shell material are more and more affected, especially those with aragonite and other metastable calcium carbonate shell material. Finally, then for the low oxygen, which we expect if the ocean warms and the solubility goes down, also if the ocean circulation becomes more sluggish, then there is more accumulation of remineralized matter in the ocean and accumulation of more oxygen. And this is a concern also for commercially exploitable fishes, and a ballpark value is 60 micromoles. Below that, it's getting critical, but this depends a lot from between the different species, but it's some kind of orientation value. So we have quite some good view on what gets dangerous for the ecosystems. We can then look at an example what happens in ocean ecosystems, and this is an example what happens if an ocean heat wave hits the region in the ocean. This is here from the 2011 heat wave hitting Australia from the work by Wernberg and co-workers. And what happened in this case, you can see this here. This is the temperature anomaly with this big heat wave here. And then at the west coast of Australia, you usually have these kelp forests, healthy corals below, and very intact ecosystem. And that tipped over here to seaweed turf. So that dominated after the heat wave, like a shock, and persisted. And this is, of course, a very critical thing. So these ocean tipping and regionally can happen very quick. This is another view on extremes. That is from a recent paper by Nikki Gruber for the area of the blob here in the Northeast Pacific, where Nikki and co-workers have looked at compound extremes. And you can see these black areas here are extremes in synchronous extremes of temperature, oxygen, drawdown, and low pH, so acidified water. And this is, of course, of concern also for the ecosystems. Choing and Fröhlicher have in this area, with a coupled Earth system model, with a coupled to a fish impact model, investigated what happened with these marine heat waves. And for the individual model ones, you can see that there's quite a good correlation. So where you have a lot of heat, you have a drawdown in the fish. At the same time, one has to be also state clearly that the mean change here in the temperature change and in the temperature and the warming and the biomass decrease of the fish biomass is the mean change is also very large and probably dominating for the impact. But then these extreme events can give an additional negative effect. I go from warming to the loss of calcium carbonate. First, we can look at the living organisms or still living organisms. One concern is the warm water corals, and they are already on the verge of, or they are very much threatened in much parts of the ocean, especially the Great Barrier Reef is in the headlines often due to bleaching caused by warming, and then an additional negative impact through sinking pH value, more acidic water. And these figures here from this paper by Högberg come from modern analogs from different places where you meet conditions in the ocean where regionally that may be more widespread in future. And you can see that from healthy, biodiverse, symbiotic ecosystems, you switch over to this kind of desert turf. On the large scale, we expect, and this is happening already, you can measure this, a shoaling of the saturation horizon, in this case here for aragonite, which is the calcium carbonate material here for corals. And then normally it's around 1 to 2 kilometers depth, and by the end of the century, for a business as usual scenario, it's getting at the surface, and there are big cold water corals as well that will vanish when this happens. So there is a big concern about these ecosystems. When we look into the sedimentary calcium carbonate, for those who are not familiar with the sediment in the ocean, the calcium carbonate is covering the submarine mountains and ridge systems like snow on the mountains and on land. So you can see this cover here in this nice paper by David Archer. And what we expect is for different levels of atmospheric CO2 and the subsequent uptake of CO2 in the ocean, a strong reaction. So we will lose by this switch from over to under saturation for calcium carbonate. It's really like a switch, an immediate switch. The acidified water will wash over these sediments and then dissolve huge amounts for a typical business as usual scenario after 10,000 years, there are about 75% of the sediment is gone, and it will return only on a very long term, let's say 40 to 100,000 years time scale. And it's also so that basically the sedimentary climate record for that time will be lost in many parts of the ocean. Then oxygen, it's a big concern because more and more hypoxic or anoxic conditions came up and in the coastal waters over the last 50 years, dominating here, especially in the east coast of the US and in Europe. And this is of big concern for the ecosystem health, but also in the open ocean, we see a widespread change and draw down in oxygen, which is relatively difficult to assess as compared to other traces because of large background fluctuations as well, but it can be clearly seen. Andreas Oschlies looked into that with a model. What happens if we today would stop the emissions, and what would happen to the deoxygenation in the ocean? So mainly the deoxygenation happens because the solubility of the oxygen in the ocean decreases under warming. So if you would do this, then you can see that the temperature of the ocean would still increase a little bit, but it's relatively on a plateau. So if you stop the emissions here, but the ocean oxygen will decline even if you stop emissions now for several hundred years until it starts slowly to recover. So it's quasi irreversible, this effect on human timescales. And what happens if you go really to anoxic regimes, especially this is of important for shelf systems with high organic carbon accumulations, and also some open ocean regions like the Gulf of Panama. If you switch from oxic to anoxic, you have a completely different world of redox regimes. And one of the concerns is that in an ocean which is has more anoxic conditions, then in these different pathways that will happen in order to remineralize organic matter, there will be more N2O produced. So the effect is that by enhancing by more anoxic conditions, one will increase the N2O emissions to the atmosphere, and this is in long-term seen a positive feedback to climate change, because N2O is a very capable greenhouse gas, and it has also the effect of neutralizing in part the input of the massive perturbation of the nitrogen cycle by converting the reactive nitrogen back into N2 gas and molecular nitrogen and N2O. But it's a big switch. So if you change these systems from oxic to anoxic, you have a completely different biogeochemistry. For the phosphate cycle, that is of concern, and this is here on the left-hand side. You see this graph from a paper by Andy Watson from Science, and it's well-known feedback feedback well known by paleoclimatologists. What happens if you put a lot of oxygen, a lot of organic matter to the seafloor, especially in shelf regions, and if you have anoxic conditions, then the involvement of the sulfur cycle and several other cycles, manganese and iron cycles, and also methanogenesis in the organic matter will produce even more phosphate that is re-released to the water column. It's a kind of vicious circle, and you can trigger an open ocean anoxic event. This is on a several thousand years time scale, but if you don't stop that process in time, it can go on and be a concern for future generations. It can be stopped probably only if you have by more wildfires and the stop of phosphate input into the ocean. But it's a big concern, and it's very well known here. For example, you can read this paper here by Meyer and Kump in the geologic literature. Very briefly, how tipping can occur in fish stocks. That's in a paper by Camilla Stuarty and others. And they looked at the Atlantic fish cod stocks and use a cusp analysis, which is kind of alternative to change point analysis, and looked at the biomass, and then the black ones are before 2004, the red dots are after 2004, and you can see that so balls at the right-hand side of the diagram show a strong overfishing rate, and temperature is increasing downward here. So you can see that the joint effect of temperature change and overfishing cause in many places more or less a collapse of the fish stocks. In some cases they are recovered, and in some cases they recover, and others is an open question whether this happens. So environmental change can trigger substantial changes in the ecosystems. I will jump over this because of the sake of time and show this figure for the glacial interglacial changes that we experienced. So long time ago, on the right-hand side, you see 800,000 years before present, and the left, the pre-industrial, and several of these climatic cycles. The black curve shows the local temperature change in Antarctica. The green curve reflects the CO2 in the atmosphere. And the ocean played a big role in this. And it's still a little bit open what caused this. There are a lot of hypotheses, and there are also in the last glaciation, you can see very strong fluctuations in the ocean circulation, the so-called Darmstadt-Oeschger events. You can also see that these jumps to the interglacials, called terminations, they are very, very abrupt. And then, I mean, there is no really one stable state. The climate system fluctuates quite wildly around. And I think we can even also learn a lot about the tipping points and reorganizations from these records still. And one has to say that everything comes together. The carbon cycle and the physics come together. About half of the feedback for the climate change is coming from the reorganizations in the carbon cycle, primarily from the ocean. Involving physics and biology, and this is probably something where we have to look into more in the future. Further issues are, of course, ENSO-log-ends, changes in the upwelling systems, sudden changes in ocean carbon uptake, and so forth. You can have a look at our paper from NPNAS last year to see more. And instead of a summary, I would like to show a table, which you normally shouldn't do in presentations, but this is a really good summary about irreversible abrupt changes in the IPCC SROC. You see a similar kind of table in the AR6, but I show this one because they are not so different. And you can see these elements which are important are the AMOC, the subpolar gyre cooling, marine heat waves, Arctic sea ice retreat, the ocean deoxygenation, and the ocean acidification. We touched upon these in the past minutes. And then finally, if you look at those which are really irreversible on a long time scale from centuries to millennia at depth, these are the ocean deoxygenation and the ocean acidification, and these are of special concern, of course. Yes, and with this, I would like to thank you for your attention, and then we can go on with the next point in the program. Thank you very much for listening.
Thank you, Christoph. If anyone has questions for Christoph, so please post them in the question and answer box. So there are already a few, but we will have a discussion session following the next speaker, so that both speakers can answer a question if they want. Oh, can you hear me?
Yes, we can.
Oh, sorry. Have you heard me before? Because I received some weird. Okay, sorry. Okay. So, so if you have understood everything, and I feel you have, since there are already quite a number of questions, but for now, it's now my pleasure to introduce Professor Stefan Rahmstorf from University of Potsdam, Institute of Physics and Astronomy. So Stefan is also head of Earth System Analysis at the Potsdam Institute for Climate Impact Research. So Stefan's work focuses on the role of the oceans in climate change. So he has been teaching physics of the ocean as a professor at Potsdam University since 2000. Stefan is a member of the Academia Europa and served for several years on the German Advisory Council on Global Change. He was also one of the lead authors of the fourth assessment report of the IPCC. In 2007, he became an honorary fellow of the University of Wales, and in 2010, a fellow of the American Geophysical Union. In 2017, yes, he was the first scientist outside the US to be awarded the Climate Communication Prize of the AGU. So it's a great honor to have you there. So Stefan, the floor is yours.
Yes, hello everybody. It's a pleasure to be part of this exciting webinar. And I want to talk about the Atlantic overturning circulation, the AMOC, and I'll jump right into it so that we have enough discussion time. This diagram already shows key features of the AMOC, mainly the surface currents in red with an overall northward transport, and the deep current in blue, the North Atlantic deep water returning to the south at about 2 to 3 kilometers depth down below the ocean surface. And obviously, this works like a central heating system with warm waters flowing north, giving up their heat to the atmosphere in the northern latitudes, and then sinking down to depth, returning to the south as a cold, deep current. Just have to click further. Yeah, here's another view of this, which is actually part of a movie animation, but with Zoom, it's not so good to show movies. So it doesn't add anything to the previous image. There was a very nice article last year in the New York Times about the dangers of abrupt ocean circulation change in the Atlantic, which I really recommend also because of its fantastic graphics that the New York Times team now has quite a track record producing great interactive internet graphics. And I want also to use this New York Times article advertising a little bit the fantastic initiative climatefeedback.org, which for those who don't know it yet, it looks at the media coverage of climate change. There's actually now also one on health issues. Together they're called Science Feedback. And what it does, it asks a whole bunch of experts in the area that is covered by some media article, whether this article is scientifically credible or not. And often they expose some really wild, unscientific climate skeptics articles. In this way, they have been able to get some retractions of wrong articles by writing to the editors of the newspapers and magazines. And this New York Times article has also been evaluated by experts, and it was given a very high to high scientific credibility rating. This is an overview of the overturning circulation caused by density differences in the ocean, which just is there to show that it's not only the Atlantic, but there is a worldwide overturning. But Christoph has already showed Wally Broker's classic image of this. This is a somewhat more elaborate, not quite as highly simplified version, which in orange shows the areas of deep water formation of the global ocean. And in green, the kind of high salinity, and in light blue, the low salinity areas of the surface ocean, because of course the density depends on temperature and salinity. And you see that the sinking happens not in the high salinity, but in the low temperature areas. So the temperature effect on density dominates over the salinity effect. But salinity does play an important role, as we shall see later on. Now, a first a very important hint on abrupt climate change comes from paleoclimatic data, notably the Greenland ice core data, which are shown here in blue. And in green, we see some sediment data from the Sargasso Sea, which show basically very similar time evolution as the temperature over Greenland, which just hints at this not being some local effect over Greenland. It's a kind of regional effect of the whole North Atlantic area, as those working in paleoclimate know very well. And the numbered events are the Dansgaard-Oeschger events, which represent sudden warmings. And the red boxes, they are the so-called Heinrich events, which basically show the release of big iceberg armadas into the Atlantic Ocean. You don't see those registered in these particular data here in the curves very, very much, except that they tend to occur during the stadial, the cold phases of the glacial. You see them in other areas, for example, sediment cores of Portugal, for reasons that I will show in a minute. The best explanation that I think we still have for the Dansgaard-Oeschger events is a sudden ocean circulation shift, and from the normal glacial state, or we could call it a stadial state, where the deep water formation occurs to the south of Iceland in the open North Atlantic. And occasionally during these Dansgaard-Oeschger events, convection starts up in the Nordic seas. And so this conveyor belt circulation, this heat transport, jumps further north into the Nordic seas. One very strong piece of evidence for this is, for example, the sudden increase in salinity near Iceland seen in the sediment cores when synchronously when these Dansgaard-Oeschger events happen. And the fact that it has to do with heat transport across the hemisphere, across the equator, is also shown by the seesaw behavior between the Greenland ice core and the Antarctic ice core, which very strongly hints at this bipolar seesaw effect, and therefore the key role of sudden changes in the Atlantic overturning. Now, when, then I won't go into the Heinrich events, but these Heinrich layers are basically showing huge amounts of glacial deposits transported by icebergs, so-called ice-rafted debris in the sediments, but they are synchronous with a breakdown of the Atlantic overturning circulation. So the idea that the AMOC can dramatically change and abruptly change is well documented in the Earth history. This has happened quite a number of times during the last ice age. Now, if we look at the present evolution of global temperature, then we see, of course, that the entire globe has warmed, but there is one notable exception that resists this warming, like that Gallic village from Asterix, and that is this region in the subpolar North Atlantic, which has actually cooled in the last 100 years or so. And just another view of this fact is this nice image of NASA that they put out a few years ago, which was just showing the temperature anomaly of a 5-year period. And while the whole globe was basically warmer than normal, this cold blob in the northern subpolar Atlantic really sticks out as a really exceptional big signal. So what is the reason for this? We can turn to model simulations for the cause of this, and here is the GFDL CM2.6 climate model, which has a particularly nice high-resolution ocean component to the climate model, which you can already see at the fine structure of the eddying there in this temperature change pattern that you see here. And it has a very realistic ocean circulation. And what this image shows is the response to a CO2 increase in that CM2.6 GFDL climate model. And you see a very peculiar anomaly pattern, and the anomaly is here defined relative to the global mean sea surface temperature change. So everything blue has warmed less than the average ocean surface. Everything in orange red has warmed a lot more than the average ocean surface. And you see this cold region south of Greenland is really very remarkable again. And some of it actually has cooled, some of it has just warmed less than average of that blue region. But there's a second part that is this excessive warming along the North American Atlantic coast. And both these phenomena of this pattern, the blue part and that red part of North America, have the same reason, namely a slowdown of the AMOC in that model. And there's a number of papers that theoretically explain why, when the AMOC slows down for reasons of vorticity conservation, the Gulf Stream moves inshore, which you can nicely see in the CM 2.6 climate simulation, but you can also see it, explain it by dynamic ocean theory and also by simplified models. So this pattern that you see here in the Northern Atlantic is what we called in this paper with Levke Cesar as a first author, a fingerprint of an AMOC slowdown. And Levke went to look at the trends in all the available sea surface temperature data sets since the late 19th century. And so she found this trend pattern. And if you look at the North Atlantic part, you clearly see this same fingerprint pattern for an AMOC slowdown, except it is a little bit more fuzzy because, of course, we don't have the super high resolution of observational data for the last 100 years or so, as we have in the climate model. But I think this is very strong evidence that the AMOC has actually already slowed down. And by comparing it to the model simulation, we calibrated this pattern to represent about a 15% slowdown of the AMOC since the late 19th century, which most of which actually has happened since the mid 20th century. In a more recent paper, again with Levke as a first author, we showed a compilation of different paleoclimatic records from around the North Atlantic. The location of these data is shown in the little map in the top right corner here. And the different curves are shown in the different panels here. The left-hand side shows about 1,500, 1,600 years of time, and the right-hand curves zoom in onto the time period since the late 19th century. And especially if you look at the longer-term evolution, you see that all these records have one thing in common. They are pretty stable up until the 19th century, and then these curves all go down, which is independent support for the idea that the AMOC has actually slowed down, because all these different publications argued that these particular sediment records are indicative of the AMOC strength, and they are of very different type, like these curves by Tornelli that is sorted silt, so it's a grain size of the sediments at the area where the North Atlantic deep water passes over the ocean surface and so on. They are very different, but they show quite a consistent picture. And we now have a little update in press at Nature Geoscience, which just zooms in onto the changes since the mid-20th century and compares these sedimentary records with some shorter term data that are trying to reconstruct the AMOC since the 1980s, or in case of the RAPID project, just measure it since 2004. And you see again that this actually presents quite a consistent picture if you account, as we did in this diagram, for time lags. The changes you see in the temperature of the subpolar gyre, or the productivity in the subpolar gyre, lag the measured rapid AMOC by 6 years. here in this diagram, whereas the sortable silt data from the deep branch lead by 6 years, which makes sense if you look at model simulations of the changes in the AMOC first appearing in the North Atlantic deep water at the bottom before you actually measure them as the full overturning signal. And so again, we see a nice agreement with very different types of approaches and data sets. And if you align them, you find leads and lags that make physical sense completely very well. So I think there is pretty strong evidence that the AMOC has been weakening since the 19th century. Now, one of the reasons for the weakening, in addition to just surface warming, is the input of fresh water. Fresh water dilutes the salinity and therefore reduces the surface density, which inhibits the sinking and thereby the overturning. And whereas temperature has a negative feedback, which means that if you warm the surface, you weaken the AMOC, which tends to then cool the surface. So there's a kind of negative stabilizing feedback. Salinity has actually a positive destabilizing feedback, because if you add some fresh water, you reduce the salinity, the AMOC weakens, and that reduces the salinity even further, because it is the AMOC which brings high salinity subtropical waters into the high northern latitudes. And so you weaken the AMOC, you reduce salinity, and that weakens the AMOC even further. And such a positive feedback, that is always a possibility for a tipping point. And Christoph has already explained in quite a bit of detail on the kind of tipping points. And he has already shown this very simple picture of a ball that is sitting in some kind of cup here, or bowl. And this is actually quite a, I think, a very good illustration of a tipping point, because that ball, if you push it a little bit to the side, it tends to roll back to its stable state, except here where the arrow points, you have a tipping point. If you push it beyond that point, it's not going to roll back. And this is also a good diagram to explain one way of looking at an approach to a tipping point, because if the landscape here, this bowl in which the ball rests, becomes more shallow, then it will take longer for that ball to roll back into its central stable position if you just perturb it a little bit to either side. And the more flat this landscape comes, the less quickly does the ball roll back, and that leads to larger fluctuations just by random noise forcing, and it leads to a longer time for these fluctuations to die down, which can be used and has been used for many nonlinear systems to indicate the proximity to a tipping point. But let me first, before I get back to this particular point, point you to this overview that we published about a bit more than 2 years ago in Nature on tipping points with Tim Lenton as the first author. And basically, we looked at a number of tipping points, updating the classic Lenton et al. Paper, which was a kind of seminal description of such tipping points. And it has there the Atlantic circulation at the center of a network of tipping points. And one of the key issues debated in the tipping point scientific world now in the community is the interaction of different tipping points, and the question, can they trigger one another in a kind of domino effect? And we wrote in this article that the clearest emergency, climate emergency, would be if we are approaching a global cascade of tipping points. And for example, for one of these cascades, the Greenland ice sheet, of course, adds meltwater. It has its own tipping point where the Greenland ice sheet will be doomed for total loss, 7 meter sea level rise, and a lot of fresh water going into the North Atlantic. That can trigger the Atlantic overturning to cross its tipping point, which in turn can trigger shifts in the tropical rainfall belts, affecting the Amazon rainforest, which has its own tipping point, or affecting the Antarctic ice sheets. The Atlantic tipping point can be very clearly found already in the most simple box models, like a Stommel type 2-box model from the 1960s. And it can be found in fully 3-dimensional global ocean circulation models. And it looks like this if you look on the x-axis at the freshwater going in, and on the vertical axis, the strength of the AMOC. Then we're now on that upper branch with a strong AMOC of something like 17 swerdrops or 18. And if we add more fresh water, we will move that point to the right where we are, and it will hit this Stommel bifurcation at some point where it will just not be able to sustain itself because of that positive salt advection feedback that I mentioned. And then the AMOC will die down, and it will not return even if you return to the previous climate. You'd have to go quite far to the left on this diagram before that off state becomes unstable and the AMOC would kickstart again. This is not something that would happen in human lifetime. If we kill the AMOC, that will be it for generations. Now, the big question, of course, is how close are we to a tipping point? And Christoph already mentioned the fact that although for many systems we understand that there is a tipping point and why there is a tipping point, it is very hard to tell where this tipping point is, because we are talking about highly nonlinear physics. And nonlinear systems are characterized by a strong dependence on the exact conditions. And so there have been many attempts in recent years to find out how close are we to an AMOC tipping point, and they are making use of that fact that when you approach a tipping point, the variance of the system increases in the presence of noise, which is always there by weather variability. And the response to that noise grows bigger and bigger as the system becomes less and less stable. Now, just by an increase in variance, you still can't tell how close you are to the tipping point. You might see, okay, the variance is increasing, but you don't know at what level of variance will you be at the tipping point until it's too late, basically. But my colleague Niklas Börs from the Potsdam Institute has published a very scary paper, I would say, in Nature Climate Change last year, looking at a number of indicators of these time series that I showed earlier, some of those from Levke's paper, Paleoclimate time series, and other reconstructions of the AMOC, like the one based on the cold block temperatures. And he has looked at this lambda parameter, which is the time it takes for a perturbation to die down, like the time it takes for that ball in that cup to roll back to the center. And when that lambda approaches zero, the time basically becomes infinite. And at that 0 point, that is where the tipping point is. And so when you look at these time series, on the left panel there at the bottom left, that's temperature-based reconstructions. And on the bottom right panel, it's salinity-based reconstructions. You see these trends since the 19th century of approaching the zero line at the top. So that indicates, according to all these time series, we are moving towards a tipping point. But this analysis also tells you how far away it is. It's when the trend line crosses zero at the top of the diagrams. And you see, of course, there is a spread between the different indicators, but some of them, like these blue curves in the left-hand panel, are reaching zero around the year 2000 already. So this is really, it has scared me quite a bit that this would indicate that the tipping point is quite close, or maybe already there even. So I haven't heard some criticism that invalidates this analysis. I would love to actually, because I don't want to believe this is true. This would be really bad news for humanity. So if you know any good reason why we don't believe these results, please tell me. Christoph mentioned that many climate models don't show this tipping point being crossed in the 21st century, but there's also a whole bunch of literature on why climate models overall probably put the AMOC in the wrong stability regime and have an AMOC that is too stable compared to what data from the ocean observations indicate. And one reason for that could be that there are problems with getting the exact salinity distribution in the Atlantic right. And a very interesting paper about 5 years ago by Wei Liu and colleagues corrected the salinity biases in a climate model in the Atlantic. So it's like a kind of a bias correction to get the correct salinity. And with that model, they found that if you take a standard global CO2 increase scenario, the AMOC does actually collapse within this century. And they call this an overlooked possibility of a collapsed AMOC in a warming climate. Overlooked because most models tend to have an AMOC that is too stable. At least that is my reading of the literature. And with that, I'm at the end, and I thank you for your attention. Sorry about the little advertisement for these books that I have co-authored, and please follow me on Twitter if you like, and also join Scientists for Future. That I think is a very good initiative, and I look forward to the discussion. Thank you very much.
Thank you very much, Stefan, for that really interesting talk, which nicely complemented Christoph's presentation as well. We're now getting lots of questions for the speakers, so please put your questions in and upvote for the ones you want to us to have the ask in the time that we have. So first of all, I've got a question. I mean, Stefan talked about the early warning systems, and so I was wondering, Christoph, if perhaps you could comment on that as well. What you think the prospects are for early warning in some of the regime shifts or threshold tipping points that you talked about?
Yeah, that's a very good question, and actually, it's we discussed this among colleagues for quite some time, and the big problem is that the observational database in many cases is not enough. So that at least for the biogeochemistry and the ecosystem part, because there exists only a very few time series, and also Argo floats are now starting to get sensors also for biogeochemical variables such as oxygen and pH and so on. And this is a big problem. So one can probably in numerical simulations get some of those, but not so easy from the observational database. And many of the time series like are in relatively stable areas. Tragically, because there you have also, if you want to observe a mean signal, that they are better for that. But in these other less stable areas, it's more difficult, and therefore I'm a bit. I think it's a little bit planning for the future how to design these observing systems that are available for this. Model runs can help there in identifying potential areas. But I think the overall the situation is still a little bit starting with identifying these things, and it's not very advanced, I'm afraid. That are my 2 cents. Maybe there are people who know better. I mean, the time of emergence of some of the signals are better for some biogeochemical variables such as carbon content in the ocean and so on, as for temperature, but still it's an issue.
Yeah, okay, thank you. That's a really interesting thing to bring in, the time of emergence and how that might relate to the thresholds. Didier, did you have a question?
Yes, thank you. So thank you for these very nice talks. Before to come to the question from the audience, so don't forget to upvote so that we can select the most popular. But my own question to start with is about the large uncertainty concerning the risk of crossing the tipping points. And I was wondering, what is your prospect about which processes of Earth system models should be improved in priority to better simulate the risk of tipping in the elements you are working on? So the question is to both of you.
Is that a question to me?
Yeah, you can start, and maybe Christoph. Yeah.
Well, you know, I can just focusing on the AMOC. I do think that the freshwater budget of the AMOC is key, and that concerns both the modeling. Of course, we have to look at the salinity biases that the paper by Leo et al. Identified as really making a huge difference to the stability. And of course, from the observation side, we also need to describe the freshwater budget of the North Atlantic in much more detail. I was actually a few years ago part of an EU proposal to do just that, but unfortunately didn't get funded. I still think it's high priority to understand these changes to the freshwater budget, which of course involve precipitation over the ocean, which is notoriously hard to measure. The river runoff, the sea ice melt changes, the Greenland ice melt. So this is quite a complex issue from the observational side. And it's also something, if you think of precipitation, for example, that is notoriously difficult to model accurately.
Thank you. And Christoph?
Yeah. So there, I think I agree that the AMOC is one of the biggest uncertainty points. But when it comes to the impact tipping points in the ocean, I think there are huge uncertainties and maybe bad surprises in the line. I mean, there is this concept also of the planetary boundaries involving both smooth and abrupt changes, and bringing together all the different global change issues, and I mean everything to do with the tipping in climate and biodiversity changes and multiple stressors, how they work together. It's still, I mean, there are big unknowns about the impact of plastic trash, for example, and on biota. We don't know. Not enough. I mean, there seems to be widespread brain damage to fishes due to uptake of microplastics and so on. I mean, there's a huge amount of uncertainties. What we know quite clearly is that the oceans will acidify, and the Earth system models can predict this quite well. There's some spurious agreement because if you plot this in the pH of the models, and they look all the same. If you plot it in a different scale, it looks different. So there is some certainty that these things will happen, and also that we will have an ocean deoxygenation. That is clear, but there are big uncertainties in the amount of what the sediments and the shelves and the shelf systems contribute. There are efforts now in including this. I mean, I think Helene is on the forefront of that with her model developments in the UK as well. There are similar developments happening in Germany and in this line. So bringing together the Earth system components, and especially also the shelf sea systems on a global scale, is one big uncertainty that has to be closed. Also in view of these very long-term nutrient involving runaway effects that may happen. And I think I'm usually like to play around with models, and very much like coarse resolution models, but the high resolution models are inevitable in order to get a better handle on the process representation for the deep water production, and this is, I mean, in most of the models, this is still quite crudely represented, and as long as we have no better really a jump in progress there, then I think there will remain quite some uncertainties on the details. Yeah, thank you.
Thank you.
Okay, thanks. So now there's loads of questions. There's 25 questions in the Q&A. So if you want to get through lots, we'll have to be, fairly succinct answers. So the first one, which is by far the most popular, comes from Jakob Dutloff, who asks, there is still a significant number of climate scientists who don't necessarily believe in tipping points, given the linear response to cumulative emissions. And so he's wondering what you would say is a convincing argument against that, and what, from your perspective, are the elements for which the tipping behavior is most certain?
Well, I think this linear response to cumulative emissions applies to the global mean temperature. And I think there is thankfully very little evidence that there could be a tipping point in the global mean temperature. But in these different subsystems that we discussed here in our talks, it's very clear that these tipping points exist. And I recommend people who doubt that to just look at the last IPCC report, which mentions tipping points in 90 places. That's up from 27 in the last assessment report. And I think they're very well documented. And for example, I think the question was which ones are most clear. I think the tipping point of the Greenland ice sheet due to the ice elevation, the melt elevation feedback is very clear and well understood. The marine ice sheet instability for the West Antarctic ice sheet is a very well understood tipping process since the 1970s. The existence of an AMOC tipping point, I think, is also very well understood, going back to Stommel in the 1960s. So, and the biological tipping point, that's not my area, but the fact that ecosystems have critical thresholds, I think is even to a physicist, that's obvious. We've had a big forest dieback in Germany because of drought threshold, basically in the last few years being crossed for many forests. And the human body has a critical threshold, when your body temperature goes much beyond 40 degrees centigrade, then you're in trouble.
Yeah, thanks, Stefan. So maybe very quickly to Christoph, which of the, I mean, you talked about a lot of different thresholds. Could you pick out one or two that you're most concerned about?
I mean, I think I don't have to add anything to what Stefan said. So I'm completely agree with him. Yeah.
Okay, thank you. So one popular question also is one from Fanny Lardy, and she wants to know a bit more how to robustly disentangle the early warning signals of a potential tipping point from the ocean or biogeochemical internal variability. So maybe you can explain a bit more how this is done. Stefan or Christoph? Stefan, maybe you talk about that a bit more with the study of bores.
Yeah, well, of course, the early warning system, these indicators, they depend on the internal variability. And the fact is just, if that variability is growing, that could, of course, have two different reasons. It could be that the noise that is driving the system, so let's say weather variability is increasing, or it could indicate that the system is getting less stable. But I think with this new indicator that Niklas Börs has introduced there, you can actually distinguish between the two. But yeah, I can't go into more detail, I think, in this setting here. You'd have to look at the paper which describes that.
Yeah, I think so.
I mean, in limited ecosystems, you can use this critical slowing down and these things and the change in autocorrelation as the papers by Darkos et al., for example, where you can look at. But the treacherous thing is that there are many tipping points that have no early warning. So where you are basically where you don't get an early warning, you can look at it from a plausibility arguments also, and just look at how far away you are, for example, from calcium carbonate undersaturation. You can look at the time series in the Iceland Sea, which shows that slowly the aragonite and calcite saturation rise in shallows, and there are other observations about this also in the Southern Ocean. And I think in the biogeochemistry, you can look at these clearly defined thresholds of oxygen or no oxygen, or calcite oversaturation, undersaturation, or a certain level of saturation, which is detrimental to some organisms. And you can see how this distance changes to these thresholds. I think that is possible. Yeah, I think that there are possibilities to do this, but for highly nonlinear systems, sometimes you get a tipping without a warning. One further thing is one possibility is also to look at the biogeographical provinces in the ocean, how the conditions for ecosystems change, and what happens to the plankton assemblages, for example, in the ocean. And there are studies starting or have been carried out, and more is coming on that. And we can see, it's projected that some of the biogeographical provinces where we have certain areas where certain organisms live, they will just vanish, and there will come up new areas with a completely different physical and biogeochemical climate on the ocean surface, and we don't know yet what happens with that. That can be tracked. But it's an open question because there are so many players involved in this. But what happens exactly? It's easier for the large scale biogeochemical changes and the large scale changes in the respective provinces, whether they are corrosive for calcium carbonate or not, or whether they are oxic or anoxic, and there it's easier. But one has to then, one difficulty is that you have to go also into the more heterogeneous shelf areas, which are not so accessible as yet for global data sets, and also not accessible for satellites, which have some difficulties with the more murky, turbid waters. Yeah.
Thank you.
Great, thanks. So a question from Gabby Hagel to Christoph is, she's just wondering how confident we are in the processes, and how well the tipping points with the ocean biota are constrained, and if not, I mean, we've talked a little bit about the Argo floats. Are there other observations we might need as well, or models?
Yeah, I mean, what is quite encouraging is what I said before about the near coastal measurements. There are more and more data synthesis, but we need more data synthesis in order to assess it. So the constraints on the ecosystems there are so many multiple facets to it that one needs a lot of observations, which we in part have. There are a lot of case studies which are quite good, and where you can see that the change is happening and has happened before, also with heat waves. There from Mantua, there are these studies decades ago available, and I think that there's quite a good constraint. And but also one more important thing will be and is now and will be in the future is transdisciplinary research in order to involve indigenous people with their experience, and we can learn a lot from that and what they see, what they observe, and what they, for example, if their fish catches change and so on. There are good ways. There are also metrics that have been developed in order to assess ocean health, the so-called Ocean Health Index by Halpern and others, which help to constrain this, but it's still a bit of a challenge to establish these metrics. In our ongoing comfort project funded by the EU, we also look in these multiple targets, and then in order to set limits and say under which condition you get in which way worse development. But this is ongoing work, and it's still a little bit of a challenge, but we are quite confident that we can add more to this in the coming years and decades, and also exploit the knowledge of people who are not directly in science for that.
Yeah, okay, great, thanks Christoph. So definitely people should follow the Comfort EU project. Didier?
Thank you.
Okay, so I have a question from Laura Jackson for Stefan. It's about the few studies that have shown that the relationships between AMOC SST in the North Atlantic might differ in different models and scenarios. And so she's asking how can we improve the robustness of AMOC proxies and reduce our uncertainty over how the AMOC has changed in the past.
Yeah, I guess if I knew, I would have already done it. It's not easy to know, to get a really good ocean model that represents the real ocean exactly as is. And of course, the models are pretty good, but they're not perfect. And it turns out that the sensitivity of the AMOC to climate change differs quite a lot between models, even though they may have quite a reasonable present day circulation. And essentially, I've worked on this for a few decades now, and somehow we haven't been able to narrow down this uncertainty. So I'm afraid I don't really know the answer, except for investing more effort in trying to get the ocean model components to get even better.
Oh, thanks, Stefan. And that sort of relates to a question from Darren Ray, who's asking about higher ocean resolution. I don't know what your personal feelings are on the prospects there.
Well, higher ocean resolution certainly increases the realism of the models as compared to observations. That's why I showed results from the CM 2.6 model, because it's very high resolution ocean. It's very beautiful to look at. It's fantastic. But the downside is that you can't experiment much with these models because they're so incredibly expensive to run. So at my department at the Potsdam Institute, we are going a different route, trying to work with coarse resolution models so that we can do a lot of experimenting, changing parameters, studying sensitivities, and doing many runs to find out where the tipping points are, etc. These are, I think, they're just complementary approaches.
Yeah, I agree. Thanks. Didier, do you want to?
Yes, so there's a kind of related question, which is popular, but not totally clear to me. So the question is from Anthony Joseph Wogan, asking, starting by saying that the IPCC have concluded there is only medium confidence of no abrupt change in AMOC. So given this relatively low confidence, or medium, do the speakers believe that we might need an IPCC special report on ocean currents or tipping points? So that's the first question. And the second one is asking maybe more details about the relationship between the abrupt cooling of the subpolar gyres, the weakening of the AMOC. So maybe the difference between the two, the link with Greenland ice loss, atmospheric rivers, found winds, etc. So that's maybe for Stefan, but maybe Christoph has also a point concerning the special report.
Yeah, I can directly comment on that. We know that there's an initiative from the TIPPES project and from, I think it was started from Switzerland, on the special report on tipping points, and it's wholeheartedly supported also from us. We have started an initiative to go through our national contact point in Norway to support it, and we have asked the members in our community also from other countries to support this through the national contact points, and we have to see whether this will come true or not. I wholeheartedly support this, but I'm a bit concerned about the term tipping point, because there are different definitions for it, and the definitions themselves are nice to structure the science, but not necessarily, I mean, they can also confuse. So we have to find out whether we call it a tipping point or critical transitions or something like that, because of this difficulty. There's a nice paper by Rosselló-Nissa in 2009 about the use of the term tipping point in the climate change community, and I recommend to read this, because then you stumble over a lot of these difficulties associated with the term. And in the end, one should not forget that probably the gradual changes for the impact are at least as important as tipping points. I mean, I don't want to have a competition about this, but when we have to consider this, and not end up in a situation where we only look at the tipping points and not the rest of the gradual changes and the more linear changes, which are clearly overwhelmingly important as well. So one has to make a correct trade-off and formulate it in the right way. And I would be an advocate to change the title, maybe not a special report on tipping points, but maybe a special report on non-linear changes, for example, something like that. But in principle, I'm endorsing that endeavor. Yeah.
Okay, thanks. And Stefan, maybe you want to comment on both questions?
On the IPCC issue, of course, the IPCC just published a special report on oceans and cryosphere a few years back. And probably there's not enough really new science on this. I think the key now is not to write more reports, but to actually advance our science on understanding these tipping points.
Yeah, I quite agree as well. And do you have any comments concerning the following of the question about the link between abrupt cooling of the SPG, weakening of the AMOC, Greenland ice flows due to melting atmospheric rivers? Maybe a bit more about processes that links the different.
I didn't really get this question, so sorry.
Okay, it's not totally clear. I agree.
Okay, well, we still had outstanding questions. Maybe if we can post those to the Miro board, then perhaps Christoph and Stefan might be kind enough to perhaps give a few responses, because really now we've just got 3 minutes remaining, and so sadly we need to wrap up. We want to give a round of applause and thank our speakers very much. Christoph and Stefan, these were excellent presentations, and thank you so much for fielding all questions. Just everyone still online for your attention and participation in the Q&A and on the Miro board. And we'll keep the Miro board active for next week, and so feel free to continue commenting and interacting there. So the next webinar in this series will focus on monsoons and will take place on the 9th of March at 3:30 Central European Time, with speakers Ashvan Seshadari from the Indian Institute of Science and Francesco Passata from the University of Quebec. The link to register is in the chat box, and if you want to get involved in TIPMIP, please fill out the expression of interest form, and the link should also be in the chat box. So that just leaves us just say thank you very much to the speakers today, and goodbye from all of us.
Yeah, thank you very much for the questions and the nice event.
Yes, thanks. It was great. I learned a lot.